Okay, let's continue with Newton's laws, and we'll talk now about Newton's second law. And it's a logical one because if you remember, the first law deals with when there's no acceleration. So this one deals with when there is acceleration. And if there's acceleration, a couple things need to come to mind. First of all, an object will always accelerate in the same direction as the net force. So whichever way the net force goes, acceleration goes the same way. And maybe most importantly is the equation. So anytime you see the word acceleration, think F net is ma. Okay, and we'll talk about that in a second. But this also leads to what we call equivalent units. That because force is in newtons, it should follow that a newton better be the standard unit for mass, kilograms, and the unit for acceleration, meter per second squared. So they're equivalent to each other. Now what that means is, if you're ever going to deal with forces, your mass has to be in kilograms and your acceleration has to be in meters per second squared. And then you can use newtons. Now, what this equation actually tells us is what determines the acceleration of an object. And if you get acceleration by itself, in this equation right here, we discover a couple of very important relationships that kind of determine an object's acceleration. The first one is between acceleration and net force. And if you'll notice, if those are my two variables, then the relationship will be acceleration is proportional to F net. And this, by the way, is assuming m stays constant. So this represents a direct relationship between these two variables. So in a simple way, the bigger the F net, the bigger the acceleration on the same mass. That should make sense. If you apply more force, you should get more acceleration. And in fact, it's more specific that if F net gets multiplied by, let's say, 5, then the acceleration should also be multiplied by 5 if the mass stays constant. And this leads to a graph where if you have F net on the x-axis, because that's what you're manipulating, and we're discovering what happens to the acceleration, a direct relationship will be a straight line through the origin. So this is a relationship between A and F net. It is direct. But there's another relationship that we can talk about, and that's a relationship with mass. We see that A now is also proportional to 1 over m. This time, this assumes that F net is constant. And so if we keep the F net constant, then we will get an inverse relationship between acceleration and mass. And what that means is the bigger the mass, the smaller the acceleration. And in fact, if we get more specific, if the mass gets multiplied by 3, the acceleration will do the inverse of that. It'll get multiplied by 1 over 3. Notice, when mass gets bigger, acceleration gets smaller. And again, this should make sense because remember, mass is a measure of inertia. And inertia is a resistance to acceleration. So if you increase the mass, you increase the resistance to acceleration. So there should be less acceleration. Okay, makes sense. And the graph, to show an inverse relationship, if mass here is on the x-axis and we discover about the acceleration, it gives you this type of rectangular hyperbola. And so you'll have to know that as well. Okay, so these are the relationships. Let's go on to the math. So we're going to do a couple of examples together. And the good news is the method is quite consistent with what I talked about in the first lesson. Here we have a block accelerating to the left, and we have a force on the right. We're looking for the second force. Okay, so when you're doing a force question, first thing you want to do is to draw a force diagram. So let's draw the block. And remember, you draw just the block. And if you want to put the mass inside, knock yourself out. Now, for the ground, please don't draw the ground as well. You draw just the block. But if you want to draw the ground, you can do it as a dotted line. But you should be drawing just the block as your system. We also know that the acceleration is to the left. Now remember, the only solid arrows you draw are forces. So this acceleration, if you want to draw it, which I do recommend, you do it away from the diagram as a dotted arrow. So here's your acceleration of 1.8 meters per second squared to the left. Now let's do the forces. We know that one force is 48 newtons to the right. So let's call that F1, and that would be, let's say, 48 newtons to the right. Now, what do you think has to be true about the other force, based on what you know in this question here? Does it make sense that F2 better be going to the left? And in fact, it would have to be bigger to cause it to accelerate to the left. So we would expect F2 to be a larger force, larger than 48 newtons, going to the left. That's what we're expecting. And let's put a reference system in here as well while we're drawing the diagram. So here's right is positive, left is negative. Okay, now, next thing we do is we state the principle. So because we see the word acceleration, anytime we see the word acceleration, that's going to be Newton's second law. And it leads directly to the equation F net equal to ma. But again, what does the word net mean? It means total or vector sum. So F net becomes F1 plus F2 equal to m times a. And to keep things simple, we're just going to substitute the numbers in now. And if you want to, you can put the proper kind of reference on the diagram itself. Acceleration to the left, so that's going to be negative. F1 is to the right, so it's going to be positive, and we expect F2 to be negative when we're finished. All right, let's put the numbers in. So F1 is going to be positive 48 plus F2 equal to, now notice mass is in kilograms. Do we want it in kilograms? And the answer is yes, we do. Kilograms is a standard unit for mass. So 15 is what we want. And the acceleration is negative 1.8. That's it. Now you just solve for F2. So we end up getting negative 75, or 75 newtons to the left. And notice that that's bigger than 48 newtons. That's what we're expecting. So it's all working out. So just keep in mind, draw a force diagram, state the law in the equation, and then solve. So just to make sure this is clear, first step, draw a complete force diagram. That's kind of step one, including a reference system. Step two is to state the law and what equation goes with that law. And then from there, you can solve the question. Good, but those are kind of our key first two steps that you will always want to do when you're solving force-based questions. Okay. And I think we have time for one more example here. Now we have a car moving forward, has its brakes applied. We're trying to find out how much time it takes for it to come to rest. Okay, so we know that we have forces involved here. So again, we want to draw a force diagram of this. Again, keep your diagram simple, just a very simple car. Nothing too fancy. If you want to draw the ground, dotted line. We know it's moving forward at 31 meters per second. That's its velocity. We can put that kind of up here. And we know that there's a resistive force on the car of 8.7 kilonewtons. So we'll just call that FR. For resistive force, make sure you change to standard units. That's 8.7 kilonewtons, which is 8,700 newtons. And again, if you want to put the mass of the car into the diagram, you can. You don't have to. Now, here's the next question for you. Notice that this object, this car, is actually moving to the right. Is there also a force moving to the right? And there's a lot of people in the world who think that if an object moves to the right, then there must be a force pushing it to the right. But remember, that's not true. Objects in motion want to stay in motion. And so this car continues to move forward actually due to inertia. It does not need a force to push it forward. And in fact, if you think about it, the only way you can push a car forward is by putting on the gas. But you realize that right now I'm putting my brakes on. You don't put the gas and the brakes on at the same time. I hope not anyways. So therefore, this is the only force acting on this vehicle to brake it. So therefore, what direction is the acceleration? And you see the acceleration goes in the same direction as a net force, so it would have to go backwards as well. And can you guys see that the acceleration goes opposite to the velocity, which means it's going to slow down. That's good when we're braking. I'll put a quick reference system in here. Let's see, to the right is, let's say forward is positive and backwards is negative. Okay, so again, there's our force diagram. Again, we want to state the law. Because there's acceleration, this is going to be Newton's second law. So have the equation F net equal to ma. But notice that F net will be Fr. That's the only force acting on the object, equal to ma, which means now we can solve for a. A becomes simply equal to Fr divided by the mass. And Fr is negative 8,700 newtons divided by 5,000 kilograms. So that gives about negative 1.74 meters per second squared, backwards. Good. Okay. So that's actually stage one. But you see what we're looking for now is we're looking for how much time it takes for it to come to rest. That's actually kinematics, you guys. So stage two is a kinematics question involving acceleration. And remember, when we typically do kinematics with acceleration, we make a list of V initial, V final, A, delta D, and T. And forgive me for scrolling up and down, but I have to for this one here. V initial. Do we know how fast it's going at the beginning? Yes, we do. It's 31 meters per second. So V initial is 31 meters per second. Positive, because it's going to the right, or forward. V final. Can you see this thing actually comes to rest? So therefore, V final will be equal to 0. We found the acceleration, negative 1.74 meters per second squared, and we're looking for the time. So displacement doesn't play a role here. We don't need that. And now we can solve the question. So the equation that does not have displacement in it is delta V over T or V final minus V initial over T. Cross multiply, solve for T. So it becomes 0 minus 31 divided by negative 1.74. Just enough space to finish that. Sig digs looks like 3. So I get about 17.8 seconds. Okay, so it is possible in your homework, is what we call an excellence level question, where we combine Newton's laws with kinematics. So you see there's really just, again, a couple of big steps here. Just want to keep emphasizing this. For the forces part, remember, you draw a force diagram, step 1, and then you state the law and the equation, step 2. And then you do as much as you can with that. And when it comes to kinematics, you make this list. And then you rock and roll from there. Good? All right, you guys know all you need to know to be able to solve the second law questions in the homework. Good luck with that. I'll see you in the next law.